Every driver heading down a long mountain grade knows this feeling. The truck starts rolling faster than it should. You tap the brakes once, then again, but the truck keeps picking up speed. And somewhere on that descent, you feel something no amount of experience fully prepares you for. The pedal isn't doing what it's supposed to do. The drums are hot. The truck is still accelerating, and the bottom of the mountain is still a long way down. This is the story of how one man's near-death experience on a California mountain pass gave truck drivers something they had never had before, a way to fight gravity with the engine itself. Early heavy trucks relied entirely on friction brakes to control their speed. Press the pedal, brake shoes press against a drum, and the truck slows as the brakes turn motion into heat. On flat ground or gentle grades, it worked well enough. But on a long, sustained downhill run, the brakes were absorbing enormous amounts of energy, and all of that energy went into heat. As the drums climbed past 500 degrees and kept rising, the friction material would progressively lose its grip in a phenomenon known as brake fade. It didn't announce itself suddenly. It crept in gradually as the temperature built, and by the time a driver recognized what was happening, the truck that weighed tens of thousands of pounds and was pointed downhill had very little ability to slow down. The runaway truck was not a rare or theoretical event in the early decades of commercial trucking. It was a recognized occupational hazard, something drivers talked about and planned around and feared. Studies from the late 70s and early 80s documented thousands of runaway truck incidents each year. As the interstate highway system allowed trucks to travel faster over longer mountain grades, states began building dedicated runaway ramps as a last resort safety measure, with more than 150 constructed by 1990. Those ramps were not a precaution. They were an acknowledgement that brake failure on steep grades was a predictable, recurring problem that the industry had not yet solved. The problem grew worse as trucks grew heavier. The diesel engine changed everything about what a commercial truck could haul. Where earlier gasoline-powered trucks were limited in both power and reliability, the diesel offered torque, durability, and fuel efficiency that made it the obvious choice for long-haul freight. As diesel engines became more powerful through the 40s and 50s, operators loaded their trucks accordingly. Gross vehicle weights climbed, trailer capacities expanded, and the freight industry discovered that a diesel truck could move more goods over longer distances, more reliably than anything that had come before. But the braking system did not keep pace with any of that progress. The same drum brakes that had been adequate for a lighter truck were now being asked to control a vehicle that might weigh 60 or 70,000 pounds on a mountain grade, and they were not equal to the task. The industry didn't accept that problem without trying to solve it. Manufacturers developed harder, more heat-resistant brake linings that could absorb more punishment before fading. Fleet operators trained drivers to use controlled braking techniques, short, deliberate applications rather than sustained pedal pressure, to give the drums time to shed heat between applications. Drivers learned to gear down aggressively before a descent, letting the engine absorb some of the truck's momentum through compression. Diesel engines, however, provided far less natural engine braking than gasoline engines because they lacked a throttle plate to create intake vacuum. On the steepest grades, some drivers would pull off the road entirely and wait for their brakes to cool before continuing. None of it solved the fundamental problem. Every one of those strategies was a way of managing brake fade rather than eliminating it, and on a long enough grade with a heavy enough load, the physics would eventually win. The man who would eventually find a real solution had already experienced the consequences firsthand. Clessie Cummins was the founder of the Cummins Engine Company, and one of the most consequential figures in the history of the American diesel industry. According to Cummins' later accounts, during a promotional drive in 1931, he experienced a terrifying near-runaway on the descent through California's Cajon Pass, an event that left a lasting impression and shaped his thinking about braking for the rest of his life. He and two crew members had set out from New York bound for Los Angeles, hauling a Cummins diesel-powered Indianapolis race car on a truck loaded to its limits with equipment and supplies. The purpose of the trip was to demonstrate diesel reliability to a skeptical public, and for the first 4 days, everything went according to plan. On the evening of the 5th day, they reached Cajon Pass, a steep and winding descent on U.S. Route 66, east of San Bernardino, California. The road was narrow gravel, carved into the side of the mountain, with sharp switchbacks and no guardrails. Cummins entered the descent in too high a gear, and the loaded truck began to accelerate almost immediately. He reached for the gear shift to drop down, but the transmission wouldn't cooperate. The road speed was already too high to make the shift cleanly, and forcing it risked locking the drivetrain. He worked the brakes instead, but the drums were already hot from the upper portion of the descent, and the pedal was giving him less and less with each application, the smell of hot brake lining filling the cab. The truck was running away on a narrow mountain road, with a full load, and no reliable way to slow down. At the bottom of the grade, a set of railroad tracks crossed the road, and as Cummins came around the final curve, a freight train was moving through the crossing. He had no room to stop and nowhere to go. The caboose cleared the crossing with inches to spare. Cummins brought the truck to a stop on the far side of the tracks, hands shaking, and later wrote that the experience never left him. For the rest of his life, he believed that the diesel engine, the same engine that had nearly killed him that evening, held the answer to the problem he had just survived. He didn't pursue that answer immediately. The Cummins Engine Company grew into a major manufacturer over the following decades, and Clessie Cummins spent those years building and refining diesel engines rather than braking systems. But when he retired in 1955, he turned his full attention back to the question that had been sitting in the back of his mind since Cajon Pass: whether the diesel engine itself could be made to slow a truck, not just power it. The concept he was working toward was rooted in something fundamental about how a diesel engine operates. On the compression stroke, the piston rises and compresses the air in the cylinder to compression ratios typically ranging from about 17:1 to over 20:1, storing an enormous amount of energy in that compressed charge. In normal engine operation, fuel is injected near the top of the compression stroke, and the heat of the compressed air ignites it, driving the piston back down with tremendous force. The engine returns that stored energy and then some. The key insight was that the compressed air, if released before combustion, represented energy that the engine had already consumed to create. If you could vent that compressed charge at the very top of the stroke before it had the chance to push the piston back down, the engine would have done the work of compression without recovering any of it. Every cylinder, on every compression stroke, would be absorbing energy from the drivetrain rather than adding to it. By the mid-1950s, Cummins had worked out the key idea, opening the exhaust valve near top dead center, so the engine would lose the energy of compression instead of recovering it. The stored energy would escape through the exhaust system rather than return to the crankshaft. Multiply that effect across 6 cylinders firing in sequence, and the result was a sustained braking force that required no friction, generated no heat in the service brakes, and could be maintained for as long as the descent required. Cummins patented the idea and brought it to the Cummins Engine Company, but company leadership saw no immediate commercial path and chose not to pursue it. He then reached an agreement with Jacobs Manufacturing, a Connecticut-based company with deep experience in engine components, and in April of 1960, the Clessie L. Cummins division of Jacobs was established to turn the concept into a production system. Officially, the system was called the Jacobs Engine Brake, but drivers quickly shortened the name to Jake Brake, a nickname that soon became common throughout the trucking industry. The engineering challenge was to build a mechanism that could open the exhaust valve at precisely the right moment in the compression cycle, using components that could be installed on existing production engines without fundamental redesign. The solution Jacobs engineers developed used the engine's own oil pressure as the actuating force. A housing mounted above the rocker arms contained a set of master and slave pistons. When the driver activated the system through a cab-mounted switch, a solenoid valve opened and allowed pressurized engine oil into the housing. As the injector rocker arm rose on its cam lobe, it pushed down on the master piston, trapping the oil and building hydraulic pressure. That pressure transferred to a slave piston, which momentarily opened the exhaust valve at the top of the compression stroke. Before the compressed air could push the piston back down, the compressed charge escaped through the exhaust system. The energy of compression was dissipated, and the piston returned with nothing to drive it. The engine had been converted in real time from a power source into a braking device. The first production units for Cummins NH series engines shipped in 1961, and the system was subsequently adapted for Detroit Diesel 71 series engines, then Caterpillar, Mack, and others as the technology proved itself in the field. What made the system so effective on a diesel engine came down to the compression ratio, A gasoline engine typically compresses its air-fuel mixture at ratios of around 9 to 12 to 1. A diesel engine compresses air alone at compression ratios, typically ranging from about 17 to 1 to over 20 to 1, which means the pressures involved at top dead center are dramatically greater. More pressure means more energy to dissipate, which means more braking force available per cylinder per stroke. On a fully loaded Class 8 truck, descending a long mountain grade, a properly functioning Jake brake could provide enough retardation to hold the truck at a steady speed, without touching the service brakes at all, depending on the grade and the load. Later versions added selectable braking levels by activating different numbers of cylinders, allowing drivers to match braking force to the grade, and the system could be sustained for as long as the descent required, without any degradation in performance, because it generated no heat in the service brakes and placed no unusual stress on any component that wasn't already designed to handle the loads involved. Drivers adopted it quickly, and the reasons were not hard to understand. Before the engine brake, descending a steep mountain pass in a loaded truck was an exercise in sustained anxiety, a constant calculation of how much brake to apply, how long to hold it, when to let off and let the drums cool, whether the grade ahead was going to steepen or ease up. Drivers who ran mountain routes regularly described the Jake brake as transformative. For the first time, they could engage the system at the top of a grade, select the braking level that matched the conditions, and ride the descent with their foot off the service brake pedal entirely, feeling the engine hold the truck back with a steady, controllable resistance that didn't fade or diminish no matter how long the grade ran. The confidence that came with that control was something drivers talked about openly. Brake lining wear dropped dramatically on equipped trucks, which translated directly into lower maintenance costs and fewer roadside breakdowns. For fleet operators running trucks through the Rockies, the Appalachians, or the Sierra Nevada on a regular basis, the economics were straightforward, and the safety benefit was something that couldn't easily be assigned a dollar value. The sound, however, was something nobody had fully anticipated. When a Jake brake is operating, the rapid opening of exhaust valves across multiple cylinders produces a distinctive staccato clatter that carries for a considerable distance. The sound comes from the sudden release of compressed air through the exhaust system on each compression stroke, and on a large displacement inline-six diesel engine running at highway speed, those releases are happening hundreds of times per minute. On trucks without mufflers or with straight exhaust stacks, which were common on older equipment and remained popular among owner-operators for the power gains they offered, the sound was amplified considerably, carrying across valleys and through residential neighborhoods with nothing to absorb it. In open country on a highway, it was simply part of the landscape of trucking. In a small town at 2 a.m, with a loaded truck descending a grade through a residential neighborhood, it was something else entirely. The complaints began accumulating as the Jake brake spread through the industry, and communities along major trucking corridors started posting signs that became one of the most recognizable fixtures of American highway culture: no engine brake, or no Jake brake, often accompanied by a fine amount. The signs appeared wherever a significant grade brought trucks through populated areas, and the debate they represented was genuine. Residents argued that the noise was disruptive and unnecessary, that drivers could use their service brakes through town and save the engine brake for the open road. Drivers and safety advocates argued that restricting the Jake brake in areas where grades existed was asking drivers to rely on friction brakes in exactly the situations where friction brakes were most likely to fail. Many drivers ignored the signs on steep grades, calculating that the risk of a brake fade event outweighed a fine that might never be issued. Fines in some jurisdictions could reach several $100s, though enforcement was inconsistent and the legal standing of the ordinances varied. The argument was never fully resolved, and the signs remain a common sight today on routes where trucks and residential neighborhoods share the same geography. What the debate confirmed, more than anything else, was how thoroughly the Jake brake had embedded itself in the culture and operation of heavy trucking. By the time communities were posting signs about it, the system had already become standard equipment on most new Class 8 trucks sold in North America. Peterbilt, Kenworth, Freightliner, and International all offered it as either standard or optional equipment, and the major engine manufacturers, Cummins, Detroit Diesel, Caterpillar, and Mack had all developed versions of the system for their own engines. The technology had moved from a patented invention to an industry standard in roughly 2 decades, which in the context of heavy vehicle engineering is a remarkably short adoption cycle. In 1992, ASME recognized the Jacobs engine brake as a historic mechanical engineering landmark, an acknowledgement that the system had not merely improved trucking, but had fundamentally changed what was possible in the operation of heavy vehicles on grades. The runaway truck ramps that still line the descents of I-70 through the Rockies and dozens of other mountain corridors across the country are a reminder of what the industry looked like before the problem was solved. They were built because brake failure on steep grades was predictable enough to require a permanent infrastructure response. The Jake brake didn't eliminate the need for those ramps. Brake systems can still fail, and drivers can still make mistakes. But it gave drivers something they had never had before: a way to hold a fully loaded truck back on a mountain grade without relying on brakes that could fade away.